on thinking about immunotherapies and building it like a hierarchical causal model. You might think about molecules within a gas and so on. Just like in hierarchical Bayesian modeling, there's so many places where we see multiple groups of data and nested data. There could be many situations in causal inference as well. Okay, so that's the idea. And in describing this work, I want to talk about three motifs for hierarchical causal models, three example models that we'll be reasoning about. Okay, so just to be clear, a hierarchical causal model is a causal model with an inner plate. Right? It's not yet clear what that means exactly, but that's the idea. I'm going to draw an inner plate of subunits within a unit in a causal model. And the three motifs we'll discuss, the first one we already did, we call it confounder. The second one is called interference and confounder, and the third one is called instrument. Okay? And so in each of these, so here are the hierarchical causal models, we're going to consider the effects of what are called soft interventions, where I am intervening on this variable A, a treatment variable, and I'm intervening on it by setting its distribution equal to something Q star of A. All right, so in a causal graph, when you intervene on a variable, you erase the arrows from its parents and replace them with your intervention. And so that's what we're doing here in all of these settings. So this is the interventional distribution that we're interested in these three different motifs. Okay? By the way, a soft intervention where we set Aij equal to some, coming from some distribution, includes hard interventions where it's set to a delta mass at whatever number you want to set A equal to. Okay, so here's the confounder graph. We already discussed this. Schools are units. Students are subunits in the schools. And we have our tutoring hours, our test performance, and the budget as example names for these variables. And the intervention is how does the distribution of tutoring hours affect test performance. Okay? The interference and confounder graph, now we've added this variable z, right, which is a unit level variable whose parents are all of the students' tutoring hours, and which has as a descendant the test performance of each student. So z might be, this is wishful thinking, but the students get tutored and then they go to the playground to have intellectual discussions, and even if a student doesn't get tutored, they might be talking to other students, and that raises the performance of everybody, for example. Okay, this is called interference in the context, that's my phone, of causal modeling. And we'll be able to reason about this graph as well. What's challenging is that this is a unit level graph, unit level variable that has subunit level parents. Okay? And then in the last case, we'll think about this instrument graph. And this is one where now the outcome variable is unit level, right? So this is no longer the test performance of each student, but it might be something like whether or not the school I is listed in a published list of top schools. Okay? Aij could be tutoring hours, and now there is an instrument variable, Zij, which might be some kind of randomized encouragement to get tutoring. Okay, and this is of course a common setup, the instrumental variable setup, but when we think this way, we'll be able to identify and estimate using different kinds of assumptions than are usually made in instrumental variables. All right, so these are the three motifs that we'll be discussing in thinking about hierarchical causal models. And so now to get into the details, first we're going to define what this means at its lowest level in a structural equation model. Then we will define a causal graphical model, which derives from the structural equation model. Then I want to describe this graph theoretic approach to doing identification and estimation in these causal graphical models, and then finally show you some small examples of taking this idea from beginning to end. Okay, so we'll start with the structural models. So just as a quick review, if you're not familiar, in a structural equation model that is described, for example, in Pearl 2009, each node is a deterministic function of its parents and some independent noise. Okay, so here's a simple example where I have x, a, and y. And you can see that each node has a function of some parents and some independent noise. called gamma A, gamma Y, and gamma X. The idea is that those are independent. They come from some distribution. It doesn't have to be the same distribution. We'll make it the same. And then X is a function of its parents, just has gamma X as its parent. A is a function of X and its noise, gamma A. And Y is a function of A and X and its noise, gamma Y. Okay? That's a structural equation model. In Pearl's world, we can integrate out the noise to produce what's called a causal graphical model. All right, so that now A, X, and Y, by integrating out the gamma variables, are random variables, and this graph inherits all the properties of a probabilistic graphical model, but because it came from this structural equation model, it's also an oracle for interventions. You can reason about causal effects in this causal graphical model. Its joint distribution is amenable to thinking about those kinds of interventions. Okay? Whereas if you just wrote a graphical model that represented a joint distribution, that's not necessarily the case. Okay, so how do we turn this picture, where we just drew a plate around students, into a structural equation model? So here is an important step. For every subunit level variable, so for like the tutoring hours and the test performance, although this is a different graph, it's got everything is observed, we're going to include 2 levels of noise. Okay? So here I turned it into a structural equation model, but now Aij, instead of having one noise variable, epsilon ija, also has a unit level noise variable, gamma ia, and every student in school I shares the same gamma ia variable when determining their tutoring hours. Okay? And so the subunit level noise epsilon captures variation among tutoring hours in each school, and gamma ia captures variation in the distribution of tutoring hours across schools. Clear so far? Okay. Here is so now I took my hierarchical causal model, turned it into a hierarchical structural causal model, or hierarchical structural equation model. I now have unit level noise independent from some distribution, subunit level noise independent from some distribution, where I have variables for each student in each school at the subunit level. And then again, each variable is a deterministic function of now its noise both at the unit level and subunit level. Xi is a deterministic function of gamma I. Aij is a deterministic function of gamma ia, that's for school I, and epsilon ija, that's for this student, and yij is a function of its noise variables and its parents. Okay? That's the procedure. All right, so the intuition here, why do we include this unit level noise on the subunit level variables? The intuition is that this captures things like hidden causes at the unit level. For example, when I draw the plate around students, maybe a school has a good teacher, and that good teacher, of course, affects all the students at the school. Right? And so these variables are assumed to be, one, non-confounding, so they're not connected to multiple variables. It's big assumptions. But they are hidden causes of these subunit variables, but at the unit level, like a good teacher. Okay, so that's how to get a hierarchical structural equation model. Now I want to play Pearl's game and get a hierarchical causal graphical model. And it's going to look a little different than the one that we drew. So again, we integrate out the noise to form this hierarchical causal graphical model, and we can do this in 2 steps. First, just like before, we integrate out the subunit level noise and produce random variables at the subunit level. All right? So the randomness of Aij comes from integrating out epsilon ij. Okay? Then we're going to integrate out the gamma variables, and that's where something interesting happens. This produces these new variables called Q, Qia and Qiy given A. And what these Q variables are random distributions or factors in the joint distribution of the subunit that come from the unknown gamma I, which is shared across all units. Okay? Make sense? So when I marginalize out epsilon, this becomes a random variable. That's simple. And now each possible value of gamma produces a different distribution of A at that school, right? Gamma I, some particular value of gamma I, produces a distribution of A. And so when I marginalize out gamma I represent that distribution as a variable in the model. And it's called QIA, right? And you can kind of see this is a little graphical model, Aij to Yij, and these are the factors that form the joint distribution in that graphical model, QIA and QIY given A. But notice a couple things. Let's see. Well, I'll just say what to notice. I thought I put it on the slides. It might be later. Notice that these Qs, first of all, X only affects tutoring performance, school test performance through QY given A. Right? In any school, let's say this is the budget affects the performance of the students on the test through its effect on the conditional distribution of their performance given tutoring hours. Right? It's through that, and this is important, number one. And number two, though these variables are somehow derived from these subunit variables that we're reasoning about, they don't inherit the same connectivity. Whereas here, Aij is connected to Yij, Qi is not connected to Qy given A. Qa is not connected to Qy given A. Okay? And this is going to be important for identification. All right, here is as a little generative process, but just to drive home the idea that these are random distributions. X comes from some distribution. Qi of A is a random distribution of A that comes from some distribution of distributions. Qy given A given X, again, comes from a conditional distribution of distributions. And then once I'm given these Q factors, the A's and the Y's, the subunit variables, they simply come from the corresponding graphical model defined by those Q's, Qa and Qy given A. Okay. And this is what I just said. The Q variables are not typical. They're distributions. They lie in between these unit level variables and the subunits, and they don't inherit that connectivity, which will be important. Okay, so any questions about this process? Yeah, please.
I'm trying to get my head around the practical example here.
Yep.
If I'm understanding this right, schools are going to set in some way that kind of unobservables their budget. So maybe they have enough budget for either 40% or 80%.
Yep.
But then within each school, it's going to be a coin flip with that given probability of which students actually get the tutoring. Is that right?
That's right. So, so here, okay, so let's say X is budget and it's observed, even though it was unobserved in the other situation. So let me walk through what you just said. So the school sets its budget and there's some randomness in that budget. Yeah? Then the school decides on how much tutoring it's going to give its students, and there's some randomness there. And then for each individual student, the school decides whether or not that student's going to get tutoring, which is somehow based on how much budget maybe they allocate, or whatever their reasoning was on deciding how much tutoring to dispense.
Well, but there's going to be no unobserved factors for the student.
Epsilon is unobserved. Yep. So there's unobserved school level pieces, and there's unobserved student level pieces. Okay. Okay. Or that is the assumption, right? The starting point here was simply saying, oh, I want to reason about students inside all the schools. And the point is with this is that when you do that, if you were going to follow the classical recipe, you would just write an epsilon ij here and be done. But this gamma is important too, because there's going to be different distributions of tutoring hours in each school. And that's what that gamma is capturing. It's capturing variation. Here, let me show you this way. It's capturing variation of the distribution of tutoring hours within each school. And it's just, I'm fitting the story to fit the graph rather than writing a graph to fit a story, just to be clear. Yeah?
So in this setting, you started without an arrow from the X to the A, right? Because before I was thinking of X as a confounder, but in this case...
Oh yeah, so in this simple graph, to describe this procedure, I'm just making X only depend on Y. But later on, we're going to have the proper budget that is Connected to both, yes.
If it was connected to both, would you have had X going to the QIA?
Yes. Yep, we will see that in the confounder case. Yep, question.
Oh, that makes sense. Thank you so much. Sorry if this is a really silly question, but in the example you mentioned of like another variable like a teacher that affects like all students at the same time.
Yep.
Could you explain like how that differs in the graph from like the budget example you gave? Like,
That's a good point. So, let me go back to this. Right, so here, well, in the budget example in the very beginning of the talk, that was connected to both A and Y. Here, this is just exogenous noise. This is something that's unconnected to anything else and just determines something about the distribution of tutoring hours. That's what the difference is. When you have a variable that connects to two things, you need to include it as a different type of variable in the graph.
okay,
Yep.
that makes sense. Thank you so much.
Okay, good. So now to your question about the budget. So now let's play the game of forming hierarchical structural equation models and hierarchical causal graphical models with these three motifs. Right, so here's the budget example, and now here I've expanded it into a hierarchical structural equation model with my two levels of noise for my subunit variables, and you see I have unit level noise for my budget variable. And here is the corresponding hierarchical causal graphical model, which looks a little different from just drawing a box because I now have these distributions that are between the subunit observations and the rest of the model. Okay, here's the interference example. I laid it out a little differently here. And here is the causal graphical model corresponding to this example. Okay, so here is my interference variable. And when I turn this into a hierarchical causal graphical model, then you can see again, I have these Q distributions for QA and QY given A. And the interference variable now still is a function of all the students' tutoring hours and affects the test performance through the conditional distribution of test performance given tutoring hours. And we're just following the recipe again with this instrumental variable example, where now I have QI of Z, the distribution of the instrument, and QIA given Z, which affects A. Okay? Good. All right, so that basically forms a definition of these hierarchical causal models. You can take a causal model, you can draw plates in them, you can connect it in all different kinds of ways, and then you can derive from that the structural equation model that you're really assuming and the causal graphical model that we can use to do identification and estimation, which is what I'll talk about next. All right, so just to remind you, in causal identification, what are we trying to do? We're trying to write an interventional distribution in terms of the observational distribution. Right? So here we are in our causal graphical model, and this is what we observe. Right? This is the data we observe, data from this model. And what we want to do is make inferences about data from this model. We want to make inferences about what would happen if I intervened on tutoring hours and set their distribution equal to QA star. Okay. So, like I said earlier, we're going to consider interventions on A in all of these motifs. And again, notice that this includes hard interventions on A if I wanted to set everyone's tutoring hours to the same number. And what we're going to do is devise a graphical procedure to do identification in this setting. So in the causal graphical models world, there are all these graphical algorithms for writing down identification formula from the assumed graph. And we're going to write down, we're going to show you a graphical way to do that with these hierarchical graphs if you have group data. Okay, so it's a little involved. First, let's just be clear what the causal estimand is. All right, and we're going to write it a little differently with these Q distributions. So remember, our estimand is simply said the expectation of test performance in a world where I intervene on the distribution of tutoring hours. But I can write that down as basically a double expectation here. It's the expectation of the expectation under Q of y in the world where I've intervened on the distribution of tutoring hours, where mu of Q of y is just the expectation of y, okay? And Q of y is the marginal distribution of y under the joint distribution of Q and A and y assumed by the model, okay? So in other words, I can write down the thing that I'm interested in as the expectation of the marginal distribution of y under the distribution of A and y assumed in this intervened model. All right? Notice, this is important, the estimand is a function only of these Q variables. All right? And so what we're going to do, I'll just tell you now, we're going to collapse out the students themselves, those pesky students, and we're going to only traffic in unit level variables, which are these Q variables, distributions of students. And that's what's going to be the lever that we use to get at some identification formula here. Okay? Any questions about this? Okay, good. So, in classical identification, you take n to infinity. You imagine an infinite number of units and that you've totally observed the observational distribution. Here, we're going to take both n to infinity and m to infinity. We're going to imagine that not only do we see an infinite number of schools, but each school has an infinite number of students inside. Okay? And what that means, this is the key, is that these QI variables, these variables that are defining the distributions of students, are effectively observed. Right? When I take m to infinity, I can perfectly estimate it. I can effectively observe these Q factors. Okay, so here's the approach. We'll do it with this simple confounder model that we talked about in the beginning of the talk. We call it collapse and augment. And what we're going to do is we are going to remove some nodes from the graph, that's collapsing, and then we're going to add some nodes to the graph, that's augmenting. Right? And the idea is to do this in such a way that in the resulting graph, we're going to have a flat causal graphical model, one that we can reason about, but it's going to have the same distribution of variables as the hierarchical model does, both pre and post intervention. And that's what's going to let us use it to do identification and estimation. Okay, so the first step is to collapse the model. We're going to write it down in terms of these Q variables. There, I just did it. And then we're going to remove the subunit variables entirely, right? Because we basically observed the Q variables, and our estimand only involves the Q variables. All right, so now this confounding model turns into this model. And it's simple because this arrow went away. Because, like I said, the Q variables don't inherit that connectivity. All right? But remember, our estimand is one about the marginal distribution of y under the joint distribution defined by these Q factors. And so the second step is to augment the model with what I call QY, which is the marginal distribution of y, which is a deterministic node that depends on QY given A and QA in each school. Right? So there we did it that way and used double arrows to show that it's deterministic. Okay? That's augmentation. So now, this is a flat graphical model, flat causal graphical model. And with this graphical model, I can do identification of the effect of intervening on QA on QY, this new node that I added. Right? So again, in the augmented graph, the causal estimand is expectation of mu of QY in the world where I've intervened on QA. And I can identify that with backdoor adjustment. Right? To be clear, the QIY given A is a confounder here through U. And so I adjust for it by taking the integral P of QY given A, P of QY given QA, and QY given A. And that's adjusting for this variable using classical backdoor adjustment. Okay? What's important, of course, is at the right-hand side, this comes from the observational distribution that we have access to, and it's a description of a causal quantity. Okay? If you do estimation from this identification formula, you get the same procedure I described in the beginning of the talk, where I take each school, estimate these conditionals, and then average them. Okay? This is just writing down how to do that. And we estimated the most trivial estimation procedure just to confirm and to show that as you see more and more data in schools and students, you get closer and closer to the true causal effect in this setting. But to be clear, this is just with simple estimation procedures. Okay, that's the first one. So now second, we're going to look at this interference graph. Here we need another detail, which is that, so now remember, we have this new node, kids talking at the playground about what they learned in tutoring class. And what we require is that the mechanism for z has to converge as m goes to infinity. As I see lots and lots of students, the value of z needs to converge to a specific value. Right? That's important because if it diverged, you would have a meaningless situation. Okay, so for example, if it depends on the mean of the aij's, that's one place where this would work. Okay? Good. So first, we're going to collapse the graph again. And now when we collapse the graph, we put in these q's, we remove the subunits, but of course we retain the connection between the distribution on tutoring hours and the schoolyard discussion about tutoring. Right? And of course we maintain the connection between schoolyard discussion and the conditional distribution of test score given tutoring. Okay? Then we augment again, since our causal estimand is a function of qy. And again, qy is a deterministic function of qa and qy given a. All right, so now we're going to try to identify p of qy in a world where we intervene on qa. P of qy where we intervene on qa. And first, we're just going to write this down directly using probability, where we have the conditional distribution of qy given qa star, the intervened qa, and qy given a, right? And that's, since qy is deterministic, this is just a point mass at the actual marginal defined by qa and qy given a. And then here's the intervention distribution that we need to target, qy given a in the world where I intervene on qa. Okay, so I'm interested in the intervention of qa on qy given a. But of course, the problem is that there's this z variable that gets in the way. So again, using Pearl's ideas, the second term can be estimated, this second term, this intervention, can be estimated with front door adjustment. It's called front door adjustment, where you condition on z and then intervene on z, but integrate out that intervened distribution. You can refer to Pearl's book or another source about how to derive that. But that gives us a handle on this second term in that integral. Sadly, this is the simplest estimation procedure for this particular causal quantity. But all it's doing is basic stuff to get at each of these terms in the formula. And again, we can see that as we see more schools and more students, we get closer to the causal effect. Okay? Finally, we can look at this instrument graph. Here the outcome is whether or not the school is in one of the top schools in the country. The A is going to be tutoring hours again, U might be budget, and Z is going to be some random encouragement to get some tutoring. And there's another step required here in this kind of method for graphically reasoning about these types of models. So first we collapse, and that's now familiar to us. We take these Q's and we remove the subunit. And so now we have QA given Z and QZ again as usual. Here, the intervention on QA is not in the graph, right? QA is not in the graph because A is conditional on Z. So now when we augment, we add the treatment variable, QA. And then deterministic outcome variables are fine, but deterministic treatment variables are sad because of positivity issues. And so what we're going to do then is marginalize out QI of Z in order to make this a random variable that's not deterministic. And we end up with this graph where we have U to QA given Z to QA to Y, where QA is defined as the marginal from QA given Z and QZ. Okay? In the end, then, we can identify P of y when we intervene on QA just with backdoor adjustment via QA given Z. And this leads to a sort of different type of instrumental variable analysis. It replaces some of the assumptions made in instrumental variables like monotonicity and additivity with other conditions. If you're interested, I have a slide at the end about those specific conditions. They're there to make sure that there's enough variation here so that we can identify the causal effect like usual. And again, we can do this and see that we approach the true causal effect against doing something naive. Okay, good. So that's the whole story, really. That's the story of drawing a plate in a causal graph and then doing something complicated and getting out a method that lets us reason about that graph in a way to identify some causal effects. So as a fun example, I don't know if it's fun, as a simple example, we reanalyze the 8 schools data. This is a classical data set in hierarchical Bayesian modeling, just to show what happens here. Okay, so this is Alderman and Powers. They studied data from 8 schools. Certainly n is not going to infinity in this data set. This data has become a staple in hierarchical Bayesian modeling. And it's similar to the running example I've been giving. We're estimating the effect of test preparation on the SAT verbal. Okay, so here's their model. They have the previous test score, Xij. They have Yij, which is student J's test score in school I, and they have Aij, which is enrollment in some kind of test prep, some tutoring, and it's been randomized inside each school. So Aij is random in each school, but might be a different distribution in each school. Okay? So first, we can imagine that there are no causal issues, right? So if there are no causal issues, then we just estimate expectation y given A. Right? There's nothing we need to do. And by the way, this is not a hierarchical Bayesian model. Right? If you do this, there's no, you're not required to put priors on anything. Could there be unit level confounders? So in the original paper, they talk about how when people were very interested in the tutoring program, more students went into the control group, okay, than in the treatment group because there was more demand. So that could be a confounder, UI, in that sense. Okay? And here, it's kind of interesting. If you reason about this graph, you recover hierarchical Bayesian modeling. You recover exactly the procedure where you have a shared prior and unknown parameters inside each school, and then estimating those parameters and estimating the conditional distribution of y given A in that setting. That is the classical hierarchical Bayesian model that paper produced. And what that says might be interesting, that causally hierarchical Bayes accounts for unobserved unit level confounding under these assumptions. But another question could be, could there be interference? So for example, class size, right, here's class size is a unit level variable, class size inside each school, will depend on how big the school is and also how many people are getting tutoring. And playing the hierarchical causal modeling game in this graph leads to a different estimate. So here is a graph where with just no confounding, this is the treatment effect that we get, that we estimate. Here is the treatment effect you estimate when you assume that there's a confounder and do hierarchical Bayesian modeling, and you can see it's a little positive. And here is the treatment effect we estimate when you do confounder and interference, and it finds an effect, a positive effect, but its uncertainty is much larger, and so it puts into question whether or not there really is a positive effect when you think about there possibly being interference here. Okay, so that's the idea. Nested data and hierarchical models are a mainstay of applied Bayesian statistics, but here what we've been doing is thinking about how to contemplate nested data in causal models. And the key idea is that that nested model, if we take n and m to infinity, really produces a flat model, but one where there are these distribution valued variables, q, that don't inherit the same connectivity as the subunit variables. What that does is open the door to identification and estimation where it would be harder if we had aggregated data, for example. That's it. Thanks very much.
Thanks, David. Questions?
Thank you so much. Thank you for your amazing presentation. I think when you were going over like the methodology, you mentioned that one of the variables, I believe it was the z variables, should converge in order for the model to be able to be used.
Yes.
For the example you gave, like how would you prove that it converges? One, and then what's the situation where like it doesn't converge? Like,
Well,
from
if
practical
z
example.
depended on the sum of the a's, for example, that would be a problem because that's, or if it was like, right, if it was equal to the sum of the a's, that would be a problem because that would diverge as m went to infinity. A is going to be positive. So depending on, for example, the mean tutoring hours is an example where it would converge.
Okay, okay.
It's a, you know, I don't want to belittle it by calling it a technical condition. It's important, and of course that model is your model of the real world, so it's a thing that you need to decide on is right. But this is a natural requirement of the model because otherwise it's hard to imagine m going to infinity.
Right, right.
It's a
Thank you.
limitation in that sense, yeah.
Thank you so much.
Yeah.
That makes sense.
Thank you. This is super interesting. So I was wondering if you could give some intuition for what the difference is between like due on the QA versus due on A. Like, right, because the causal effect you're estimating is expectation of y condition on due QA. So
Yeah.
you're intervening on like the distribution of treatment rather than like the treatment itself, right?
Right. So right. That's right. So this is a limitation in the sense that, right, we're not considering interventions on particular students. So you can't say things like, I want to take the top student and not give them tutoring. We have to be intervening on the distribution of tutoring hours for the students. Now, one could intervene on each student and give them all, give him or her the same number of tutoring hours. You can do that because that's a point mass QA, but otherwise it needs to be a distribution. So that's the distinction. Similarly, you can't ask causal questions about individual students in this setup.
Should I think of this as like you're looking at the causal effect of a treatment policy rather than like a treatment itself?
Yeah, that's a good way to put it.
Thanks.
Hi, David. Thanks for the nice talk. Just to follow up on that question, and I think this may have been what Avi was asking, I'm inferring. I'm not sure I can describe it precisely in the context of your examples, but can the policy depend on features of students?
Yes.
Such that I can condition on those features and the errors epsilon become IID or something like that?
Yep. Eli, my co-author, would have wanted me to include that in this talk, but I argued against it, but yes. I should have. So the intervention can depend on an Xij. It can be a conditional intervention in that sense. So then, while you can't talk about individual students, you can say, you know, the students that are, whatever, have a grade point average higher than this, we want to give them tutoring with this probability, and the students with a grade point average lower than that, we want to give them this other distribution of tutoring. Absolutely.
Any other questions?
Why does it have to be so complicated?
Well, actually, even that, when you said it many years ago, wasn't that complicated. But I think the same question arose in my mind as it was here. Have you thought of specific methods of checking the sensitivity of your assumptions?
Yeah, so this is really as far as we've gotten, identification and some simple estimation procedures. And what we want to look at now is, in the context of real applications, think about better estimation procedures or think about the properties of the estimation procedures, and then think, of course, about sensitivity. We haven't thought about that. It's very important, of course, in a causal pipeline to think about. Right, I'm describing the variables that are there, but of course the assumptions lie in the variables that are not there, and understanding whether or not they're really absent is important. Yeah.
Any other? Maybe I have one question. It's to the other extreme. So here, maybe a few more concrete examples. Is there more general abstract theory? I can think about this where you have a general graph and then just general identification result, general estimation result.
Yeah, so these are examples of our general theory for reasoning about graphs with plates where you take two variables to infinity. Is that your question? If there is?
Yeah,
yeah.
I'm trying to figure out for general one, is there an abstract version of the algorithm that's...
Yeah, there is. So for example, here's the way you collapse, right? And then augmentation is still case by case in the sense that you need the variables in there that are related to your causal estimand and understand what they are dependent on inside this collapse graph. And then identification in that flat model comes from the do calculus. Yeah.
Thanks. Okay, maybe we can take the rest of discussions offline. Thanks, David, again for amazing
Thanks
talk.
very much.
Thank you.
Yeah.